Scalable waste gasification. Turning waste into energy. When you recycle your household waste, it may go a little something like this. You put the wet gloppy stuff into a compost bin, you clean the paper, plastic, glass, and metal as best you can, and put them in a bin, or maybe separate bins. You move the bins to the curb, where a truck picks up the bins, swallows their contents, and drives the stuff someplace where you hope it's put through environmentally sound processing. You don't know if that place is within a few miles, tens of miles, or hundreds of miles from your house. However far away it is, you can be sure that energy is consumed to get the waste there and get it processed. And pollution might be generated to transport it, even if the waste ends up in a landfill anyway. The recycling processes and markets for compost, paper, glass, and metal are pretty well known and work pretty well. Not so much for plastic. That's because different types of plastics require different handling and recycling. Some plastics just hang around, which is bad because we make and use plastic much faster than we recycle it. We wouldn't use plastic if it weren't so versatile and durable. It's light, strong, and clean. We can do so many things with it that it's hard to imagine not using it. Plastic is often the only way certain food, medicine, and other stuff can be packaged to get into third world countries. Even if we stop making plastic today, there is so much in the environment now that it will be hundreds of years before it's gone. But maybe we don't have to wait that long if we use a process called small-scale microwave-induced plasma gasification. What? Yeah, I know. We'll explain more later. For now, let's just call it waste gasification. As we talk about scalable waste gasification, keep in mind that no method of energy generation and no method of trash disposal can be a universal solution applied everywhere by everybody. But it can be applied in many situations, maybe even yours. It's a way to take in plastic waste and output energy. All we can reasonably ask is to derive as much energy as we can, save as much energy as we can, and get useful work done with that energy while polluting as little as possible. In these next sections, we'll explain a few core concepts and then describe a possible solution, a small-scale device for converting waste to power. We'll be covering these topics. Pyrolysis. It's not incineration. Pyrolysis starts with pyro, a slang word for someone who loves to set fire to things. So, it's easy to think that pyrolysis, fire, burning, and incineration are all the same thing, but they're not. Fire appears during combustion. That's when a substance combines chemically with oxygen from the air and burns, spewing out flames, heat, and smoke. But in pyrolysis, there is no fire or smoke because there's no oxygen. In order to keep out the oxygen, pyrolysis is done in a container that holds only the substance, but little or no air. So, instead of burning, the substance decomposes into simpler molecules that can then be reformed in a controlled way without releasing pollutants to the open air. So yeah, pyrolysis and incineration both involve heat, but they are different. Like pyrolysis, plasma is used in waste gasification. We'll see how later, but plasma is a pretty interesting topic all by itself. Stuff we see every day, like water for instance, can be a solid, liquid, or gas. As you heat ice, it melts into a liquid. Heat it more, it turns to steam. But what if you heat it even more? You get what's called plasma, the fourth state of matter. Plasma is the most prevalent state of matter in the universe. The surfaces of stars, like our sun, are plasma. It's even common on Earth. Lightning is plasma. A plasma is made up of huge amounts of free electrons and positively charged ions, or cations. Like a gas, a plasma has neither a defined shape nor volume. Though most gases are electrical insulators, plasma is an electrical conductor because it consists of charged particles. Hence, a plasma reacts to electromagnetic fields and conducts electricity. Typically, a plasma is made by heating a gas until its electrons have sufficient energy to escape the hold of the positively charged nuclei. As molecular bonds break and atoms gain or lose electrons, ions form. Plasma can be made using a laser, microwave generator, or any strong electromagnetic field. So plasma. Yeah, it's weird, but natural. Gasification is a process for extracting a gas from a substance, or converting a substance into a gas. Why would we want to do that? Because gases like methane can be used to power electrical generators. There are lots of ways to gasify a substance. We're going to look at pyrolytic gasification because in pyrolysis there's no fire or smoke. That's because it's done in a container that holds only the substance but little or no air. The substance decomposes into simpler molecules that can then be reformed into a gas without releasing pollutants to the open air. In a way, pyrolytic gasification is recycling at a molecular level. We're turning molecules of plastic into molecules of a synthetic gas, or syngas. It's mostly methane, which can be cleanly burned to power electric generators. Almost any substance can go through pyrolytic gasification, even biomass like plants and wood. We're going to focus on plastics because that's what we're trying to get rid of. Plastics are carbon-based polymers. A polymer is a long-chain molecule composed of many repeated instances of a smaller molecular structure. A plastic can be made from petrochemicals or natural materials like plants. If it is made from natural materials, it is called a bioplastic. A petrochemical plastic and a bioplastic with similar chemical compositions will have similar properties. A plastic item, whether it is petroleum or plant-based, can be disposed of by degrading it. That is, breaking apart its molecules into simpler molecules. Degrading methods include exposure to UV light, mechanical processing, and chemical reactions. Another method is biodegrading. In biodegrading, living organisms do the breaking apart. If a plastic is engineered to break down more quickly, it is called biodegradable. Bioplastics, which may or may not be biodegradable, are made from sugarcane, cornstarch, potatoes, or other plants. These plastics are made from polylactic acid, and so they're referred to as PLA plastics. A different type of bioplastic is PHA, which stands for polyhydroxyalkanoate plastic. PHA is a unique polyester made naturally by certain bacteria. Unless it is engineered to be so, a petrochemical plastic is not biodegradable. Certain bioplastics are also not biodegradable. Even biodegradable plastics may persist in the environment for decades. For example, PLA plastic takes 3 months to degrade in an industrial composting facility where heat and oxygen are applied to speed up the composting process. Though certain PLA plastics can degrade in only 3 months without such processing, most PLA plastics that go into a landfill instead of a composting facility can persist for decades or even hundreds of years. So, with all of the types of plastic waste that there are, degrading it for disposal involves a lot of transporting, sorting, and processing. A better way to handle all kinds of plastic may be to recycle them at a molecular level using pyrolytic gasification, because you can put in any kind of plastic. No matter what kind of plastic you put into pyrolytic gasification, what you get out depends on the temperature and how long you heat the plastic. In this table, you can see that as temperature and time go up, you get more gas. After about 1,000 degrees centigrade, it's all gas. That's because heating causes chemical bonds to break down and electrons to go rogue. In fact, if you really crank it up to say 1,500 degrees centigrade, you get a cloud of electrons and positively charged ions. That is, a plasma. When the temperature is lower, say 500 to 600 degrees centigrade, the process is called cold plasma pyrolysis. Cold plasma produces highly energetic electrons that break down the chemical bonds of plastics, but uses less energy than full-on plasma-induced pyrolysis. At those lower temperatures, pyrolysis is not completely free of pollutants, but there's less pollution than other processes, and because they are in a closed container at normal pressure, the pollutants are easier to scrub out. Plasma-induced pyrolysis takes place between 1,500 and 4,000 degrees centigrade, so it uses more energy and may require fancier cooling. But at those temperatures, almost any kind of material breaks down. Toxins and organic poisons break down into safer materials. In both cold plasma and plasma-induced pyrolysis, chemical reactions take seconds instead of days or years, so the temperatures do not need to be maintained for long. Whatever type of pyrolytic gasification we use, we can recycle molecules of plastic into a gas that can be used for power and heat, and it doesn't matter what kind of plastic it is. If we want to recycle the molecules of a plastic into a fuel gas by using pyrolytic gasification, we need a way to heat the plastic in a closed, gas-tight vessel. We're going to need to heat the plastic to temperatures ranging from 500 degrees centigrade to 4,000 degrees centigrade. We could use gas, electric, infrared, or plasma arc heating, but let's go with microwave heating because, as we'll show, it's the most versatile solution. Microwave heating works on what are called polar molecules. A polar molecule is electrically neutral, but has a positive electric charge and a negative electric charge that are spatially separated, so it acts like a molecular electric compass needle or dipole. Like a compass needle, a dipole orients itself to the polarity of the field it is in. If the polarity changes direction, the dipole rotates to change direction with it. That may not seem like a big deal, but at 2.45 gigahertz, the frequency at which a microwave oven works, the field is alternating, that is, reversing its polarity, 2,450 million times per second. At that rate, the dipole rotates back and forth so fast that it transforms the microwave energy into heat within the molecule. Though not all plastics are polar, we can get microwave heating to work by including some polar plastic in the vessel or by adding a polar substance like water. Even with that, the heating happens pretty fast. Think of how quickly you can heat a snack in your kitchen microwave oven. An industrial microwave oven works the same way. Like a kitchen microwave oven, we can easily control the temperature and time of heating. And the plastic is heated more deeply and completely than it would be if we were to use, for instance, hot air. Plus, microwave heating allows us to heat the plastic without having any heating elements in the vessel itself. An industrial microwave oven is compact, quiet, and clean. It can be precisely controlled and can be turned on and off instantly. Because a microwave oven is electronic, it can be computer controlled. Feedback systems, instrumentation, and data logging are easy to implement. In a microwave oven, a device called a magnetron generates microwaves. A solid-state microwave generator can be used in place of the magnetron to make the oven quieter, more efficient, and more reliable. A solid-state microwave generator also makes it possible to use software to adjust the frequency for optimal coupling, which maximizes energy transfer to the plastic. Adjusting the operating frequency changes the locations of hot and cold spots in the plastic. Sweeping through the frequency range moves the hot and cold spots around to electronically stir the plastic for more uniform heat. With appropriate focusing techniques, the hottest plastic can be kept in the center of the vessel and away from the vessel walls. The plastic in the center can be heated until it becomes a plasma, a ball of plastic-eating lightning in a bottle. At the start of this video, we talked about how we recycle our waste at home. Gloppy stuff goes into a compost bin. Paper, plastic, glass, and metal go into other bins. Bins get picked up and transported for tens or hundreds of miles to a place that may or may not do environmentally conscious processing. But what if we applied what we just learned to design a small-scale, microwave-induced plasma gasification system and process? We could save the energy used to transport the plastic, we'd prevent the pollution from the transport vehicles, and we'd generate energy we can use at home. An implementation of the system could be assembled by connecting a microwave induction gasifier unit to a tank for storing methane, which fuels a natural gas electric generator. The electricity could go directly into your home's electrical system or be stored in a battery pack for later use. Except for the microwave induction gasifier, all of the components already exist and can be purchased and adapted to the system. For example, we could start with a small 40 kilowatt household backup electric generator. The microwave unit would include a cylindrical vessel that can handle the high temperatures, perhaps made of a ceramic. A microwave generator would be placed so it could be aimed at the center to heat the plastic from the inside out, so that the coolest plastic is against the vessel walls. The methane is pumped out as it forms and piped to the methane collection tank. When there's enough methane, the natural gas generator turns on and generates electricity that's conducted through a converter into the house's electrical system, or into a storage battery array. Whatever plastic is not converted in processing one batch can go into the next batch. A scrubber could be included to remove residual pollution, or sensors could detect toxins and pollutants, pass the data to the system, and the heat in the gasifier could be increased to decompose them into safer compounds and elements. In this system, 10 kilograms of plastic could be converted into enough electricity to run a desktop computer for over 150 hours. Here are the cocktail napkin calculations. 10 kilograms of plastic yields about 9 kilograms of methane. 10 kilograms is about 22 pounds. 9 kilograms of methane works out to about 16.24 cubic meters of methane. A 40 kilowatt backup generator uses 15.29 cubic meters of methane per hour. So, if we fuel the 40 kilowatt backup generator with 16.24 cubic meters of methane, the generator will run for a little over an hour. That works out to 42.49 kilowatts. Let's say that running the system consumes 12.3 kilowatts. That leaves 30.19 kilowatts. A desktop computer uses about 0.2 kilowatts per hour. So with 30.19 kilowatts, the computer will run for about 150 hours. We each use about 185 pounds of plastic waste per year, or 15.41 pounds per month. For a family of 4, that's about 60 pounds per month. Since 10 kilograms is about 22 pounds, you could probably at least run your computer with the plastic that accumulates in your home. Even if we only used it as a backup system, we'd be ahead because the plastic would be disposed of without transportation and external processing costs. And consider the savings on natural gas. The cost of natural gas varies, but let's say it's $3.25 per 1,000 cubic feet. A 15 kilowatt generator costs $1.71 per hour to run and consumes 245 cubic feet of natural gas. During a power outage, the generator costs around $20 to $40 a day to run, depending on the energy load. We can start by building a small prototype. The microwave generator parts could be pulled from a kitchen microwave oven costing $350. The vessel could be a ceramic microwave oven kiln costing $135. A used standby generator could be purchased for less than $500. Add in a tank, storage battery, electronics and controls, piping, and other small parts for an additional $1,200. That comes to $2,185. More if we have to buy it all new, less if we can borrow the parts or get them for free. Once the prototype achieves an acceptable level of performance, it could be used to process plastic as a service to make a little money. That money could be used to hand build a few more units. The units could be deployed in selected homes to make a little more money. That money could be used to design and build a manufacturable unit. We'd have to do some market research, but let's say an acceptable price for a manufactured unit is the combined cost of a clothes washer and dryer, plus a water heater and backup generator. About $3,020. So let's say then that the unit would need to be manufactured for $1,300. Can we get to that price? Probably. Most technology gets cheaper over time, and by selling large enough quantities of the unit, the cost per unit would likely go down. Assume for now that we can do it. Imagine what could be done with a small-scale microwave-induced plasma gasification unit. It may seem that scalable waste gasification is not dramatic or disruptive, but that's a good thing. Except for disasters like tornadoes and floods, most natural processes happen slowly, a little at a time. That's how to develop and deploy scalable waste gasification. The parts of it, like waste processing and pyrolysis, are not new. In fact, devices and processes similar to those in scalable waste gasification are popping up all over the world. The nonprofit Dung Beetle project in South Africa is probably the closest thing to what we're talking about. To learn more about it, visit their website. As with that project, we are starting small. By doing so, we don't need the hundreds of millions of dollars that large-scale municipal and industrial waste disposal and energy generation projects require. We also don't have to slog through years of getting approvals, permits, and such. Instead, we can use our time and money to refine the design to make it more efficient, perhaps by replacing the natural gas generator with a microturbine. The battery pack could be replaced by flow batteries. Meanwhile, the system could be scaled up for apartments and small businesses. When we have enough data and money, the technology can be adapted to handle other kinds of waste, even sewage or industrial and medical waste. When the technology is ready to convert multiple types of waste into energy, it can be used to clean up the debris at disaster sites and generate power for the victims. Neighborhoods, cities, and countries can use the technology to save money on energy while cleaning up their environments. As small-scale waste gasification gets accepted and spreads across the country and maybe even the world, it can provide jobs in engineering, manufacturing, installation, maintenance, repair, inspection, sales, marketing, and who knows what else. So, waste gasification can scale up pretty big.